right, here we go. Okay, so as you can see, the multiple choice, not really multiple choice, but it's easier to read this way. We saw pretty good introduction on the second attempt. The average ended up 79%. I'd actually like to see that second one up in the mid-90s. So, you know, if you can bump that up next time further, that'd be great. This part was 70.7, gave us a 149.4 out of 200. So that's like what, almost 75%. All right, so that's good. What else was I going to say here? I'll post. Okay, let's quiet down, please. I'll get a key posted and then remember, as it says in the syllabus, you'll have, once I get that posted, you get a week to look over your exam. I'm going to pass them back at the end of the class today. Get a week to prepare your exam to key, and if you see anything that you think is questionable, then you can come and see me about it. Okay, but we want to take care of all those things in a reasonably quick time, and don't stack them up and come to a big stack exam right before the final or something like that. Yeah, that's what you got there?
Yes. So what do you do for appointment? What do you mean?
Usually you'll have the exam, so if you want me to take a look at it, you should come in and see me, either office hours or email me about your time or something like that. Okay? All right, any other questions? Okay, then. We are going to finish up chapter 16 today. So this is a chapter on conjugation, resonance, and dienes. So somebody, if I forget, somebody remind me there's 10 minutes left in the class, and I'm just going to lay these exams out on the floor and have you guys come fight for them. Okay? But remind me, sometimes I just get so enthusiastic to get going, I just don't remember. We finished off on Friday. Okay, let's quiet down. There's too much talking. Talking about the addition of a hydrogen halide, HBr, to a diene, a conjugated diene. And what we found out is that we get two different types of products. One called the 1,2 addition product, and the other one is the 1,4 addition product. If we change the conditions of the reaction, particularly the temperature, we can sometimes get different ratios of products. Okay? At low temperature, the reaction is irreversible, and the product distribution is controlled by the differences in energy at transition state. So it's all rate or kinetically controlled. We found out that the fastest product formed is always the 1,2 addition product. Okay. If we put more heat into the reaction, sometimes we give it longer. With more heat, the reaction becomes reversible. And so we essentially have kind of an energy sink at that point, and we just get a higher proportion of whatever is the most stable product. All right? And judge the stability based upon the stability of the alkene that remains in the product. So the more highly substituted that is, the more stable the product will be. Okay? So we had a couple of steps. The first step is to know where to protonate the diene. We're going to do another example. We have to protonate it, like always before, to give us the most stable carbocation. At low temperatures, we always get the 1,2 addition. At warm temperatures, we have to judge which possible product is more stable. Okay? So that's kind of how it works. So we're going to look at one more example of this type of addition reaction, and then we'll look at another reaction, the Diels-Alder reaction. Okay? Yeah, question.
So before you mentioned that with the 1,2, the halogen go to the closest carbon. What does closest mean? Closest to the
Well, so what happens, here, let me just draw something out here. So if we were to, if we had a diene like this, and this gets protonated, remember it typically gets protonated on one of the end carbons. So we could draw out, so our HBr here, right? And so the first step is going to be protonation of this double bond. Okay? When we do that, we end up with our new proton attached here with a plus, and our bromine is still kind of floating right here next to where the H is. Okay? So the closer one is going to be the one where remember the plus is spread between these two positions of the allylic carbocation. So the proximity effect says that the bromine is going to more easily and more quickly bump into the carbocation part of the diene or the allylic carbocation that's closest. So it's 1, 2 instead of the other end. Okay? All right, everybody got that? All right, so let's start out with a clicker today. All right, let's try one more example. All right, so take just a second and see if you can figure out where you would protonate this diene. All right, so let's just kind of arbitrarily label these different carbons. All right, so which of these carbons would be the position that picks up the H+? How many people think number 1? All right, 2? Nobody? 3? 4? Okay, so remember what we have to do. We want to really protonate at either 1 or 4. Okay, because if we protonate on one of the outside carbons, it gives us a allylic carbocation. If we protonate at 1, then we get a carbocation here. So this comes up this way. Let's just draw the mechanism down here. We get an allylic carbocation like this, right? Starts out tertiary. What's going to be the substitution of the other contributing resonance structure? Is also going to be tertiary, right? Okay, so the other structure would look like this. Okay, so this is going to be the most stable carbocation. Remember, this is a single carbocation. And the 1, 2, and 1, 4 addition products are always going to come from the same allylic carbocation. Yeah?
So in terms of the 1 to 2 product or the 1 to 4 product, in this case, would they both be as equally stable? Or?
Well, let's draw them out and see. Okay? So the 1, 2 product is going to come from the first carbocation that we drew. So this would have bromide reacting with the carbocation here to give us this product. Right? So this is the 1,2 addition product. The 1,4 addition product would come from this other one. Okay, which would be this. All right, so that's 1,4. So which one of those is more stable? They're both the same, right? Yeah, question.
Do you also get a mixture of stereochemistry for each of the products?
Okay, good question. What do you think? So we have in both cases we have a carbocation, right, which is in conjugation with this other double bond. So we essentially have a p orbital on each of these 3 carbons, which is our allylic system. When we have a planar carbocation and we have a nucleophile react with that, should we get a mixture of stereoisomers? Yes, because both the top and the bottom are essentially equivalent, right? So we would get a racemic mixture of a single product in this case. All right? So, you just have to be able to work through it. The key here is not to memorize anything here, but you want to work through the problem and then evaluate the products. Okay, so this is 1,2, 1,4. These are, in this case, actually the same. So it doesn't matter how we change the conditions, we get the same product. And this would be, like we said, racemic. All right, so you just go step by step, figure it out. Okay? All right, so let's... Well, this is just a summary of what we've done. Here we're going to look at the Diels-Alder reaction, discovered by 2 German chemists, and they shared the Nobel Prize for discovering this reaction. All right, so it is a reaction of diene. Just got a simple one here. And we could think of it as an electrophilic addition reaction, just like we've been doing. But here's the product. Like this. All right, so is that what you would have guessed?
No.
No, maybe not. It's probably not what they thought either. Okay, so how does this actually happen? So, well, first off, we got to figure out, when we look at the product, where did the different carbons in the product, how do they correspond to the reactants? Right, so we see this R group right over here. So obviously that's this R group over here. So the way we would break this up is that the R group goes with this piece right here. Okay, so we've essentially formed this bond and this bond right here. And we kind of bumped, over to here. This is the piece that came from the diene. So essentially, because the double bond is in the middle of what that diene was, it's essentially a 1,4 addition to that diene. Okay? So how does this actually happen? All right, so this reaction is kind of cool. So we're going to have to orient the diene like this. Yeah, question?
So can this happen with isolated dienes?
Okay, so the question is, does it happen with an isolated dienes? No. This is only for 1,3 conjugated dienes. Okay, dienes, at least like this, that are kind of acyclic, not in a ring, have 2 possible conformations. Remember, we talked about that there's a partial double bond character between the double bonds due to resonance. Okay, but it can rotate, but it takes some more energy. All right, and so we have 2 possibilities. We have one, like that top one, where the double bonds are kind of pointing apart, and this is referred to as S-trans. And I don't know really where this came from. They're kind of pointing in opposite directions, so trans is kind of opposite. And this one down here is called S-cis. Okay? And all the only difference is that it's rotating around this carbon between the two double bonds. All right? Turns out that this S-cis, this is the required for the Diels-Alder reaction. Okay, so if, for example, the diene is in a ring or something and it cannot rotate and adopt this S-cis conformation, then the Diels-Alder reaction will not take place. Okay? So the way that we usually do this is we just line these groups up like this, and we can just push the electrons around in a circle. Okay, so I'm going to show it kind of like this. This could go, let's do it in red, this could go over and react with this carbon. So it's a pi bond reacting. This pi bond could go over to react with this carbon, and this pi bond shifts right here. Okay, so it's all a concerted reaction. Okay, what does concerted mean? Yeah, it's all in one step. All the bond breaking and bond forming is happening simultaneously. Okay, so when we do this, right, let's look at how it all changes. We just have to map this out. So here's kind of the carbon skeleton that we started out with, right? And I'll draw in red. We've formed this sigma bond right here. We've moved the pi bond, so the new pi bond is over here, and we've formed a sigma bond over here. All right? So in general, this Diels-Alder reaction is a way to make these cyclohexene rings. Okay, though there's some variation that we could have as well. Okay? So the way that we push this, the electrons around here, we haven't really, we're going to talk about this in the next chapter, but maybe you've seen it before. It's kind of reminiscent of benzene. Maybe you saw this way back in the chapter 1 or something, where we talked a little bit about resonance. And so we can actually have a resonance structure with benzene where these electrons just move to the next position. And so both of these kind of processes are pretty similar. And the transition state of the reaction would involve this six-membered ring. And because that's a nice, stable ring size, this is a favored reaction. All we have to do is heat this thing up. We don't add anything else to it.
Question?
Yeah?
So what would happen if you had like a 6-carbon diene? Would it be able to react?
Okay, so the question is, what if we had a 6-carbon diene? So it depends. It has to be a conjugated diene. Okay, but what we'll see as we go through some examples is we don't have to only have 1,3-butadiene. Okay, we can have different groups attached, and they'll just be attached to this cyclohexene. Okay? All right, in fact, different substituents. Okay? The best way is if this R group right here is an electron withdrawing group. Okay? And so here's R, and different electron withdrawing groups, they would be things like, it could be, say, a ketone. So all of these kind of electron withdrawing, what they're going to do is they're going to pull electron density away to one side, and they're going to essentially polarize this reactant. So we'd have O minus like this, and plus at this end. So what we've done is built up a delta plus and a delta minus. So if we're doing this electrophilic addition reaction, and we have something like this, we have a delta plus, delta minus, it makes this position with the delta plus be more electrophilic. Okay, so it's short of electrons. It attracts the other electrons more strongly. Okay, so we can have things like that ketone. We can have esters. We can have, actually we can have nitriles like this. These are all considered electron withdrawing groups based on resonance. Okay, and these will make the reaction more, well, react faster. Okay? In fact, they don't tell us this in the book, but we can do the opposite thing as well. And if we put an electron donating group on the diene, that will make it more reactant because it would make it more nucleophilic. Okay, so electron withdrawing group on, here I gotta label these. This is the diene, of course, we know this already. But this other, this alkene that reacts with is called the dienophile. So it just loves dienes, right? Phile means it loves it. Okay? So dienophiles are most reactive if they have this electron withdrawing. Okay, so let's look at some variation. Okay, so let's look at that top one. Right, so we've added some methyl groups on the diene. We have an ester on the dienophile. And so the way to figure these out is just to redraw it so the diene and the dienophile are facing each other so we can push the electrons around. All right, so let's just redraw them over here. So we have to redraw the diene in this S-cis conformation. It has the two methyl groups on those two center carbons. All right, and then we're going to draw the dienophile, and in this case, the diene is symmetrical, so we could draw the dienophile with that R group or this ester being either on the bottom or on the top. Doesn't matter. Okay? So then, what we're going to do is this is going to go to here because this is the delta plus end. Right? So we have the nucleophile reacting with the electrophile. This pi bond is going to go over here. This one is going to go over here. And then we just have to figure out what this is going to give us. We're forming our ring. Shifted the double bond here. We have the two methyl groups there and there. And then on one position here we have, running out of space, we have our ester right here, CH3. Sorry about that. This is oxygen. Oh, there's plenty of room up here. I'm on the edge of my screen over here. I'm wondering why I'm trying to squish that into a big open white space. All right, so that's just the same ester that I have in the diene file. Okay, so again, the diene and the diene file can either, react one on top of the other or the other way around. So we would end up, we have a single stereogenic center, so it would be a racemic mixture. Okay. All right, let's look at the next one. Look at that. The diene now is in a ring. Okay, but notice that it's in a ring, so it's locked into this S-cis conformation. So that still works. So let's draw this out. I'll try to make it a little smaller so I have some room. Okay, we're going to aim the diene at the dienophile, which is just ethene this time. Okay, so this pi bond is going to react with one end of the dienophile. This double bond is going to go over here, and this is going to shift here. All right, and we can draw this product in a couple of different ways. One way is just to draw it like this, and then we have to kind of draw this piece across here. Okay, so it's a bridged compound. Okay, so we have a 6-membered, so you can see that it's cyclohexene that we formed. And then the CH2 group here on the end is bridging over the top. Yeah.
And that only happens for cyclic dienes?
Yes, if we have cyclic dienes, then we end up, this is called a bicyclic structure. A bridged bicyclic structure. We can also draw it this other kind of fancy way to give us an idea. And this thing is bridging up over the top like this. Okay, so there's our cyclohexene, and the CH2 goes up and over the top. All right? Let's erase that little part. All right, look at the bottom one then. We can do Diels-Alder reactions not only with the dienophile being an alkene, but we could do it with alkynes as well.
Question for you.
Yeah.
Shouldn't that be a cyclopentane?
From this piece here? Yeah, so here's the cyclopentene. It goes this way, and it goes up over the top, down to here, and over to here. All right, so here I can circle it. So here is the cyclopentene. Okay, so this is the part that comes from the diene. And this part right here comes from the dienophile. All right? It's tricky, huh? All right, so let's think about the bottom one. Okay, so I'm going to use up some extra space here. So again, we're going to aim the diene at the dienophile. Okay, and here we got two esters, both electron withdrawing groups. Okay, push the electrons in the same way, see what we come up with. Okay, so this is going to react with one end of the alkyne. This goes over to here. This goes over to here. Okay, so what's going to be different about this structure? Right, it's going to have two double bonds left over because we have the alkene that comes from the diene, and we have, because we had two pi bonds in our dienophile, only one of them are reacted. We have one left over. Okay, so then we have one ester over here and one ester over here. And and again, it shows plenty of space for you guys, but I don't have the space here. I don't know why it's doing it like that. So we get a diene, an isolated diene, though, in this case, in our ring.
That's big.
Yeah.
One quick question. With the previous example with the cyclic diene, if the dienophile was cyclic, would we get the same product, or?
Well, no. If the dienophile was cyclic, no. Well, we certainly get a different product, right? So there are examples like that. I don't know if I have one here. Let's keep going.
Okay.
There's some.
What would we get a racemic mixture for the last one we did? Like, because there would be two double bonds. So
Right. If there's two double bonds, so is there on that example? Is there a stereogenic center? No, there's no stereogenic center, so we get a single product in that case. All right, so in this case, let's look at the possibility of we have two different dienophiles. They're the same, but they just differ in their stereochemistry, right? So we have a cis dienophile and a trans dienophile. All right? When the reaction takes place, just like before, we draw the arrows. What we observe is that if we start with a cis dienophile, we get these two substituents. Oops. So this is another way to draw an ester. Will remain cis. Okay, we get cis there. This is cis over here. Okay, so the stereochemistry of the dienophile is maintained through the reaction. Okay, the bottom one is only different in the stereochemistry of that dienophile. And so if we start with trans, we get trans. All right. So would, in both of these cases, would there be an enantiomer that's formed as well? No? Well, let's draw them. So we could, they could come together in the opposite way. We could get this one. Or from this one, we could get it opposite as well. Okay. What about that top one? What's the relationship between these two compounds? They're the same. Okay. And why are they the same? Right? This is that situation where there's a plane of symmetry down the middle. We call this meso. Okay, so we get a meso product because there's a plane of symmetry down the middle, so the two mirror images are the same, even though there are more than one stereogenic center. What about the bottom one? What's the relationship between these two? These are enantiomers. Okay, and so in this case we would get a racemic mixture. Okay. All right, so I just have more slide. Okay, so here's another cyclic diene, and so I'm going to try to draw this like this. Okay, we're going to imagine that that's coming in here, and then the dienophile could react with this in two different ways. Like this, where, let's see, this can react with this side, this can react with this side, and this goes over here. Okay, so the point is that this ketone is underneath the diene. Okay, and so then we get something that looks like this. This is bridged again, but it has something like this. Okay, and this position has an H on it and the ketone, like this. So we could have that, or these are kind of hard to draw. We could have this one go like this, oops, and be sticking up this way. So it's pointing away from the diene. So this goes here, this goes here, and this goes here. Okay, so in either case, the diene and the dienophile come like together like this. So what I'm trying to show, like if the ketone, it could either in the top case, this is the diene, the ketone is pointing underneath the dienophile versus pointing away. Okay, so this case would give us something that looks like this. With the ketone pointing up this way. Okay, so there are different stereochemistries at this center. In that case, it's, oops, I didn't draw the extra double bond in there. There's a double bond right here. Okay, this one, because the the substituent is pointing towards that alkene is called endo, means towards or underneath here. And this one is pointing away, this is called exo. Okay, and it turns out that in these cases the endo product is favored. Okay, it's because the p orbitals here can kind of interact with the diene underneath. They kind of stack on top of each other. Okay? So there's some more examples of these in the text. So of course work through that Learn Smart thing and look at the examples in there. Most cases we just want to push those electrons and see what we come up with.